My name is Tessa. I'm from the University of Pennsylvania. I'm one of the co-moderators from this session. We're going to go ahead and get started with this afternoon's program on artificial intelligence and outcomes research. It's my pleasure to invite our first speaker to the podium, Dr. Kalpathy-Cramer from MGH, speaking on how to teach a machine.
Thanks for the opportunity to speak here. So as everybody here I'm sure knows, machine learning seems to be absolutely everywhere these days, whether it's tagging faces on Facebook or machine translation or self-driving cars. Obviously, even in radiology, we see a lot of it mentioned in the news in lots of places. For those of you who were at RSNA last year, there was a pretty exciting session on deep learning and a pretty good debate about whether radiologists are going to be replaced by machines or not. So in terms of opportunities for machine learning, so the things that we can probably hope to teach a machine to do are things in the areas of quantitative imaging. And so in quantitative imaging, in the screening setting, so one of the areas that some people are very interested in is seeing how to get the machine to read in low resource settings, for instance, in places where they don't have enough manpower and resources. Can we get the machine to at least do triage and identify those people who might need to go see the next level? In terms of personalized medicine, choices of therapy, is a patient responding, things like that, again, potentially machine learning has a lot of room to play there. And then quality improvement. Can we get more standardized outcomes? Can we get things to be more, to improve essentially the quality of our task? So just very briefly, machine learning is often classified into things like supervised or unsupervised learning. In supervised learning, what we typically tend to do is have a lot of data with known outcomes, and this could be labels in terms of whether this is cancer versus not, or whatever disease versus not. And then we use that examples to teach the machine what it is that we are trying to predict. In unsupervised learning, we don't really have any kind of ground truth, so to speak. We just look for patterns in the data. And so we try to see how can we cluster people, or how do we cluster disease presentations, things like that. In supervised learning, we can look at things like classification. Again, this is trying to, for diagnosis, for instance, of, again, is this benign or malignant? Is it stage 3 or stage 4? But we can also use it for regression. So if we have something that we want to try to map onto a severity scale, can we use the machine, again, can we teach the machine to predict a value of disease severity, for instance? Typically, in terms of how we do this, we can create a set of rules and essentially have the machine follow along algorithms or kind of a set of trees or a decision tree and so on. That's on sort of one end. On the other end, and this is what is getting really exciting and more common these days, is just show the machine lots and lots of examples. Without really saying what it is that you're doing, you show lots of positive cases and lots of negative cases. And the machine seems to know what it is that essentially distinguishes them. There have been some really fun examples of teaching machines to do things in the non-medical domain in terms of teaching a helicopter to fly, for instance. It learns to fly just by watching examples of other helicopters flying. So self-driving cars, they learn from what other humans have done in those situations and try to learn what it is the correct behavior should be. So the idea is that if you have lots of data and lots of different presentations of the data, and if you show that to a machine, it can essentially learn to identify those key attributes of the data that help you make those decisions. So just taking a step back, often radiology has been a little more descriptive or qualitative in terms of, you'll often see statements about heterogeneity or speculation and things like that. And what we're really hoping to drive to is getting to a more quantitative place where we can, essentially everybody's reporting on the same set of attributes and has the same metric that means something tangible. I'm going to take a slight detour into this area called radiomics that's become, again, was very popular in the last maybe 5 years, where the idea is trying to quantify the findings in the report and using features and other attributes beyond perhaps what a radiologist may report. So an example from mammography is if you're talking about a mass, there are things that you would want to be in the report about things like the shape, the size, the margins, the density, and so on. So again, this is what the examples of what the shapes might look like, what the margins might look like, and typically all of this is done by a radiologist using words. The idea is, can we use math somehow to try to describe these features and then figure out which of these features are actually predictive in making the kind of decisions that you want to make. So the field of radiomics and radiogenomics, which has been, again, around at least since 2012, and was a really hot topic sort of prior to deep learning in the last 2 years, was the idea with that was that you take your images, you identify your regions of interest, you potentially render it in 3D, and then you extract features. And these features can be things about the shape, the size, the texture, and so on. And then you build, using these features, you build a predictive model, and then use that for disease prediction and so on. And these features, again, have things about the shape descriptors, size, intensity, and so on. And so you might be able to distinguish things that have high sphericity, low sphericity, this concept of texture. Does it look more, is there a lot of heterogeneity within the object you're trying to map? All of that was what the field was doing prior to the last few years, and where a variety of factors have come together to sort of really propel the concept of deep learning in image recognition. A lot of this has come from the computer vision field, and the availability of 3 different aspects have really made a big difference. So hardware, in terms of GPU computing, has really advanced in the last 5 years. Again, the computer vision community has been really good about making available open source software frameworks. So these frameworks allow pretty much anybody to build on what other people have done, and that's all open source, so you can get the software. And then the final thing has actually been having access to lots and lots and lots of data. So somebody actually took the time and effort to label street scenes. So these were cats and dogs and airplanes and so on, and created millions of images that have labels. And using that, people were able, the machines were able to get to essentially identifying objects in regular scenes. As to why that is important for us, what's been surprising is that the same approach that is used to detect a cat and a dog, or in videos and things like that, the same things can actually seem to have value in radiology. So using essentially the same architecture and even the same features, as at least at the lower level, that were used for these other domains, seem to have value in our world. So in a more traditional framework, we typically tend to have a clinical question that we're trying to answer. We find some retrospective data, we process them, we may do some image registration, we do some segmentation, we typically handcraft the features, we classify it, and then try to predict. In deep learning, we sort of skip all of those things and start with just the image, and essentially have, as long as you have lots and lots of labeled data, you can get to your prediction without actually having to say, oh, I think these are the features, these are the attributes that I think are important. So essentially, a deep learning network is a neural network that has a lot of input features. It has these things called hidden layers and the output layers. And the things that go into the input features are essentially pixel values, and then these hidden layers are some kind of mathematical aggregation of the value. So a weighted sum of the things that the previous layer become the output of the next layer, and so on. And when we started off in the 90s, we had maybe 2 layers because that's what the computing capability allowed us to do. The most recent networks have 150 layers. Again, because of the GPU computing capability, we are in a place where we can do lots and lots of these calculations very effectively, and allows us to push lots of data through and get much better outputs. The most classic example is digit recognition, where you essentially take your images of digits and transform them to intensity values, and then you get a predictor as to whether it's a number from 1 to 9. You can do essentially the same thing with a lung nodule. You feed it to, take in a whole bunch of lung nodules, take essentially the pixel values of those nodules, feed it into the network, and out comes a prediction as to whether it is benign or malignant. In terms of resources, there's really cool toys out there, websites. There's this thing called TensorFlow. There's a playground where you can actually see what these networks are doing and how they change as a function of your input. So here's a classification problem. You're trying to separate the blue from the orange, and you want to come up with a boundary that does a good job of that. So you can create these neurons, you can feed the data through, and soon after some time, you get something that looks a really nice separation between the blue cases and the red cases. If you didn't have enough neurons, if your network was not sufficiently complex, you can come up with boundaries that are not good enough. If you have lots and lots of neurons, you can come up with essentially very complex shape decision boundaries that can try to mimic the data that you have. In terms of what these layers and networks are learning, surprisingly, we find that they're actually learning somewhat meaningful things. The first layers tend to be learning things about edges and sort of very basic things that we look at when we look at an image, find areas of differences between parts of the image. The second layers tend to aggregate these features into more sums of those, like in this case, in face recognition, they might look at eyes and nose and mouth as separate layers, and then the final thing, you come up with faces. The same sort of thing we see in our radiology images. The first layers tend to be more about edge detectors and things like that, and then as we get more and more down the chain of layers, we get to more comprehensive features that we're looking at. So you take an image, you feed it through the network, it predicts whether it's a dog or a cat. You do the same thing sort of with lung nodules, and it comes up with an answer as to whether it's benign or malignant. In terms of opportunities in radiology, as I was just mentioning earlier today, I was at the ISMRM conference in Hawaii a couple weeks ago, and there was, again, a tremendous amount of excitement about the opportunity for deep learning. What was really exciting there was actually on the acquisition and reconstruction side of things. So deep learning is having tremendous impact, not just on once you've acquired the images that we're used to seeing, but in looking at case-based data, for instance, or much more going back along the acquisition chain and getting back to the rawest of data, and then using that to improve the reconstruction, to find disease, to find pathology, and so on. It's been used a lot for segmentation and quantification. One of the problems with deep learning, or one of the challenges in medical imaging, is that we need lots and lots of well-labeled data. It can be very difficult to get that for a variety of reasons. In the case of segmentation, though, what we really have is lots and lots of pixels or voxels. So if you can imagine we have tumors segmented, because we don't have lots and lots of patients, but we have lots and lots of voxels that have been labeled, we can get pretty good segmentation with very small, relatively small amount of data. It's used for diagnosis, detection, virtual biopsy. Some exciting work recently is in trying to predict, for instance, IDH status. Can we look at an image, feed it through a deep learning network, and have it predict IDH or MGMT or a variety of biomarkers of interest? And can you find similar patients to what we're doing? So again, tumor segmentation has been used. Deep learning does a really good job with segmentation. We've been running this brain tumor segmentation challenge for a while, where the goal is to segment the brain tumors into various subparts, including edema, necrosis, and enhancing area. We have publicly available networks now can do a really good job of essentially doing the segmentation. So this is the virtual biopsy. Can we predict the mutation status? So essentially, going back to the question of how do we do this, we need to really rigorously define what is the problem that we're trying to solve. Is it the classification problem? Is it a regression problem? Is it a detection problem? What specifically is it that you're trying to do? And then we want to get lots and lots and lots of well-annotated data. And the question of what lots is varies in the domain. If it's segmentation, maybe a few hundred cases is plenty. If it's classification, many hundreds is good. Lots and lots is in the computer vision, people use millions. I don't know if you're going to get there here, but even with a few hundreds of thousands of data sets, we can do a lot. Get a machine with some GPU, pick a framework that you want to use. Are you something that is GUI based? Do you want to write code? How comfortable are you with all of that? Train the network, validate, and iterate. One of the complaints that many people have with these black box solutions is that it's a black box. We don't really know what it is that the machine is doing. So there's been some interesting work in this area of saliency maps. So the idea of the saliency map is essentially you're trying to identify what part of the image is it that is leading to the decision. So you occlude different parts of the image to see which part causes a decision to flip. And it's been actually, they've done it in ophthalmology, in standard vision, and in radiology. And the networks actually seem to identify the areas of interest. So it's not entirely random what the network is doing, or it's not not that we cannot interpret what the network is doing, but the networks seem to find the areas of concern that lead to the question. So this is an example with the GUI-based. This is a digits product from NVIDIA, for instance. You just essentially point it to a folder of images that are labeled as plus and minus, and it does its magic and predicts the answer. On the other hand, if you want to write code, there's many different options in terms of how easy or hard it is. But in general, the community has made all of this so easy to do because of the open and friendly nature of the community. In terms of sort of hybrid processes, people occasionally do segmentation using deep learning and then use handcrafted features. People are very, for instance, want to measure things like the margins, the volume, the shape, and the size. So you can use the deep learning for the segmentation part and then go to the handcrafted features for something else. People stack models on top of each other. So you have one model for segmentation, and then a different model for the feature extraction, and then a different model for the classification. A recent challenge that I think Mark will touch upon a little bit, there was a large nodule lung screening challenge that was held by Kaggle using the National Lung Screening Trial data. Some of the best models had submissions had this two-stage process where in the first stage, the system would identify all kinds of candidate lesions, and in the second step, it'll classify those candidate lesions as being malignant or benign. So these models can be stacked that way, meaning you get a model for each step, and then you sort of filter through a funnel of these things. You can also sort of combine models. Some of the best results are using different models for each, for instance, for the segmentation or for the classification. So you create a bunch of different models, and then you put them together. And for a variety of cases we've seen, and this has been true for machine learning for a very long time, is that often an ensemble of models outperforms any particular model. So this is an approach that seems to, again, hold true in some of this work we're doing. In terms of the challenges for medical imaging, our data tend to be big. We have 3D, 4D, 5D, and many D data. Most of the models that have been used in computer vision have been based on 2D RGB images. How do we transform those models to the kinds of data that we have? Obviously, we need lots of data, and then there's questions of privacy. We have unfamiliar, unwieldy formats. The hardest part is getting good ground truth and annotations. A lot of what we find is a substantial inter-expert variability. So when you're training a model, you need to have consistent data. The noisier these annotations are, the more data you need. Often disease lies in a spectrum, and people have different internal thresholds for where things go from one bucket to the next bucket. When that buckets are slightly different, and you put all these data together, you get very noisy looking data. Or if you train on one person who tends to overcall things and then validate on somebody who tends to undercall things, you're going to get poor results. And it's not that the model's inherently bad, it's that this disease is not a binary outcome sometimes. The interpretability of the models is important. The question is, will black box models be accepted even if they work really, really well? Or do we want models that may not work as well, but you can understand what they're doing? We talked a little bit about the acquisition and scanning protocols. The appearance of the images can change substantially, so having models that are robust to that is interesting. And then essentially we want to get to the goal of more general systems. So often what we tend to have is we have a model for one kind of disease, and then another model for another disease, and another model for another disease. And when you really want to say, is it normal versus not, or is it sort of a general system, how do we train models that are not very disease-specific but tend to be a little more comprehensive? And then how good is good enough? If we have a machine that's as good, if you cannot separate a machine from the difference between two radiologists, is that good enough? Or should machines be held to a much higher bar than humans are? When you talk again about interpretability versus accuracy, does it matter? How about continuously learning systems? So if in some of these models get better and better with time, but they're not the same model that was used at one point that will be used again. So how do we deal with that? Do we want to freeze our models, or do we want to allow for some learning, continuous learning in the models? So I just have some resources for anybody who really wants to sort of play with this. It's great fun out there. Again, because of the community being so open, there's lots and lots and lots of resources out there. So with that, thank you for your attention.
Thank you for that phenomenal talk. I'm pleased to introduce our next speaker, Dr. Tarik Alkasab from MGH. He'll be speaking on clinical decision support for radiologists' future.
Awesome, and thank you to the organizers for the opportunity to come speak to you. This is a topic that sort of brings together a lot of the aspects of a lot of the exciting aspects in radiology right now, and that I'm very passionate about. And these things really should have, the Facebook option of it's complicated. So I don't have any real financial disclosures in the sense of any financial stake in anything, but our department has a relationship with Nuance Corporation, and I do work with the Nuance Corporation, advising the Nuance Corporation as part of that agreement. Although, as I said, I have no financial stake in any technology or product that's relevant here. So one of the, I'm going to start by describing one of the challenges that we face, which doesn't seem to have anything to do with machine learning or artificial intelligence, which is the problem of helping radiologists do better at applying known standards to their practice. So I'm sure almost everyone in this room who's a working radiologist has seen this flowchart. It is the management flowchart for incidentally discovered adrenal nodules that Link Berland and his group published as part of the ACR's Incidental Findings Committee in 2010. And this tells radiologists what the best reasonably current evidence is on how we should be directing the management of these incidentalomas. But the problem is that Lincoln's group came up with that terrific flow chart, but it's not very integrated into the radiologist's workflow. The radiologist is, doing his or her work, but if they come up with one of these situations, such as an adrenal nodule or any of a few dozen, or probably, if we started thinking about it, a few hundred other known, very standard clinical scenarios, there's a known, correct, agreed-upon way in which we should be reporting these, including making recommendations, but not just making recommendations, features and data that we should be including as part of those. But in order to remember what those are, it can be tricky, and so radiologists either have to remember what it is or go look it up, or, and this has been so far the best technology we've had, we scotch tape it up next to the workstation, right? And surely in this era of digital radiology, we can do better than scotch tape. And so at MGH, we set out to develop some technology to do this, and we've managed to create that and get it promulgated and help the ACR develop its own standards around it, which are now starting to be adopted, and which I'll describe briefly to you. So the first step is to turn one of these guidelines, the output of a standards group, into a machine-readable format. And so this lays that out for you. So this is an example of what that might look like. So you have a section that describes the relevant features or pieces of data that need to be extracted in the scenario, and then a description of the logic, and then a description of what actions should be taken depending on the outcome of applying the logic to the values of the data points as the radiologist supplies it. And so the goal is that instead of a group that is drafting some kind of practice guideline, stopping with just creating a white paper and a flow chart, that they would actually have created as part of the output of their group, a standard format way of describing exactly what data elements, what logic, and what exact actions are intended to be carried out as part of that. And now all of that is being encoded in a community-owned schema known as ACR Assist. So the ACR, and this is going to be prominently described at the ACR annual meeting, where I suspect many of you will be the week after next. And you can also find it on ACR's website. We'll be publishing the official definition of how a description of one of these should look, as well as documentation. A white paper will be coming out in JACR shortly, as well as a piece of open source software that you can download and use. If you create your own XML files, you can see how the interaction with those work. And then in addition to that standard, the ACR will be starting a process of identifying its own internal content, such as the incidental findings papers and the various RADs that could be turned into or made available in this format, so that they could be used by various vendors within their products. And so that's something that we're going to be talking more about at the ACR meeting in a couple of weeks. So what does it actually look like? So what if you take one of these things and you actually had a reporting environment that was set up to actually provide it for the radiologist at the time that they're drafting their report? So while the radiologist is making their report, if they got to the point where they needed to describe an adrenal nodule, there'd be a way to bring up probably at least in our prototype implementation at MGH, a window that lets the radiologist describe the features of what they're seeing. So in this case, you can see the various components of it. And the key thing about this is all of this is being driven by that XML file, that blob of code that, for example, the ACR could have produced to describe exactly what's wanted when a radiologist is working up an adrenal nodule. And none of it has to be encoded into the reporting software, into the software that's actually running at the time the radiologist is doing their report. And so the radiologist, fills this in, and as they add more information, it changes the recommendation you see the generated text that's being created, and then finally the radiologist says insert into report, and the text automatically becomes inserted into the draft of the report that the radiologist is making, and they can go back and change it as they need to, and so on. Another example of more recent technology, a radiologist is drafting a report on a pelvic ultrasound. They see a cystic lesion in one of the adnexa. They bring up the tool to describe it. As you know, the Society of Radiologists and Ultrasounds guidelines for management of ovarian cysts relies heavily on the radiologist matching what they're observing to one of about a dozen standard imaging patterns, and using this tool we can actually show the radiologist those imaging patterns along with some features, and the radiologist basically uses this as a pick board to say what pattern what they're observing most closely represents, and then they pick that and it puts the appropriate information and recommendation right into their report for them. And there could be more advanced examples like this for things like systems for staging lung cancer, for staging rectal cancer, for grading trauma, any kind of place where what the radiologist is saying about something should be standardized, and we know how we're supposed to do it, but the exact details of exactly how we're supposed to do it remain something that can be difficult to remember or something that can be difficult to stay up to date with. And that's, I think, the real key, is that we can provide these tools for the radiologist at the time they're reporting to let them see exactly let them have access to these tools, let them have access to these guidelines, especially in these places where it's almost incidental to what they're doing, to make it easier, to give them a set of rails to run their report on for the specific clinical scenario that they're seeing. So why is this helpful to the radiologist beyond that broad idea? One of them is that it provides a standard of care and lets us create more consistent reports, which is known to be desirable from our referring colleagues. And then, although I always refer people about this to Ben here when it comes up, it arguably creates a medical legal safe harbor for radiologists to be able to demonstrate that if you used this tool that you were certainly following a standard of care in how you made, or more importantly, as we think about how this could be used to reduce costs, didn't make a recommendation for follow-up imaging. And then it provides a way of demonstrating quality, a way of documenting quality, and that can become part of financial incentives or our relationships with payers, with our partners, for example, in accountable care organizations, and then also with the feds. So as MACRA and MIPS become a bigger part of our life, being able to find ways to actually demonstrate what it is that we're doing and how we're doing it better and how we're doing it with high quality are going to become very important to us in ways that are actually meaningful, as opposed to the meaningless abuse of the prior regime for providing incentives to radiologists. But I think to the people in this room, probably the largest motivation is that this kind of system is going to help the radiologist bridge what I call the data divide in imaging, which is summarized by this: that we collect all of this rich data in pixel data in the studies that we perform. And on the other hand, in the clinical side, it's becoming more and more important that patients are managed according to the actual clinical data that's available in the data stream. But the way we actually take those pixel data and push it into the clinical data stream for our patients is we draft a radiology report. And our radiology reports are essentially blobs of prose text in this country in English, which is frankly a terrible way to be transmitting information. And as a result, there's a ton of information that's, first of all, that actually is in the radiology reports that is relatively inaccessible. But I think even more important, radiologists, as they look at that pixel data and interpret images, are building up a mental model in their heads that contains a ton of potentially valuable information about the patient and the results of the study that is not being captured at all by this prose report, and finding ways to capture more of the information, capture more of the usable clinical information that the radiologist realizes and thinks of into the clinical data stream would be incredibly valuable. And so the way that we are moving toward doing this, the way that the various reporting vendors are moving toward doing this, is creating the concept of what we call a data layer. So in addition to the prose report, which would maybe be kind of what's presented as the official result, a radiologist could also be extracting pieces of data that could then be transmitted into the medical record. So these would be things that would be create a flow of data from the pixel data to clinically usable pieces of data, which could then take their place especially in the patient's electronic medical record, and used to drive further downstream decision making. And I think that then we think about where's this data going to come from. And obviously, there are going to be a bunch of things directly from the scanner, some things entered by the technologist, some things which are machine extracted, some things that the radiologist creates at the time they're doing it. And the idea is that the ACR Assist technology will take its place as one of the tools that helps the radiologist do that in as expeditious a way as possible, so that the radiologist doesn't become what I like to call a data entry monkey. I think that would be an unfortunate development, but I think it is important that the data that flows from the pixel data into the clinical data stream do so over the radiologist's signature, that we take strong ownership of that process, even if during a transitional phase it involves us being more like those data entry monkeys that I worry about us being. And then obviously the electronic medical record can play a role in that as well. So what might this look like in actual practice? So let me give you an example of how this might work. So this is one of my favorite clinical scenarios. I work clinically as an emergency radiologist, and so if you twist your ankle on a Friday evening in Boston and you end up at the MGH ED, I will probably be the person reading your ankle film. But if your plane lands in Boston on a Friday evening and you're a little short of breath and you come to the MGHED, they will almost certainly order a PE-CT on you, and so I will be reading that CT. But now I'm imagining a future in which we have data-enabled the process of reading this CT, and not only that, used the process of this data-enabled CT as a route for bringing in machine learning tools which might have been developed into the radiologist's work stream. Because I think that's one of the really key parts of this vision, is that this kind of data layer and the assisted reporting that enables it is going to be basically the route by which data such as would be extracted by the kinds of tools that Jayashree was just describing to us and that Mark is going to tell us more about in a minute, will find their way into, first of all, into the radiologist's hands, and then more important, into the downstream management of the patient. So I'm imagining that what would happen is that even before I realize that the patient has had a PE-CT, that there will be some AI server of some kind, maybe on site or maybe not, that will go and extract the images from the PACS and then perform its magic of the kind that Jayashree talked about on it, and extracts from it some features which it will then package as a small blob of data, which can then be injected into my reporting environment, so that my reporting tool, whatever it happens to be, is going to be aware of the fact that a machine learning tool has run on it and made some information available to it, and know what the outputs of those are, know what it has found. And then when I actually go to open the reporting environment and I start to create my report on this PE-CT, what can happen is that can send a signal to the PACS, and the PACS can then, my PACS viewer can then access that information that in that data context that the reporting environment has put together, and bring me right to the appropriate images and show me the image and point out the feature that was extracted by the machine learning tool, and then maybe even ask me some other questions about that, ask me to verify the finding or something like that. And then when I do that, it can send the result of that interaction with me back into the data context of the reporting environment, which can then say, hey, the radiologist confirmed there was a PE on this. You, the AI server, there's another task that you should run on it, and then it can get the images again, or maybe get some more images, and maybe do a search for evidence of right heart strain on the CT images and send a report back to that, and then that can prompt a different kind of interaction with the radiologist in the reporting environment, where we bring up an assist tool to ask the radiologist to grade the overall clinical scenario, including evidence of right heart strain, and then all of that can be automatically inserted into the prose part of the report, and then when the report is finally sent over to the electronic medical record, that can be sent, both the prose parts that the radiologist has created, but also an extraction from that big data context that has been built up by the reporting environment over time as part of the official record of this examination for the patient. And then, of course, different subsets of the data that were generated as part of creating this report could be sent to a research registry or to a population health registry. For example, a recommendation that a radiologist creates can be encoded in this data layer, and then that can be included in a population health registry to make sure that, for example, if the patient had a pulmonary nodule, that they were receiving appropriate follow-up for that. And then, of course, we can send an extract of those data to to a national registry, both for further outcomes research, but also for automatic tracking of compliance with federal incentives. So the motivations, in addition to the previous ones I talked to you about, center around kind of this flow of data. So specifically being able to integrate data from not just scanners and assistants in the electronic medical record, but also as a real interface point for the artificially intelligent tools that the other speakers here are telling you about in a way that I think is going to be very important. And then second, for making data available to downstream systems. So for example, as I said, structured recommendations, data for registries of various kinds, data to drive imaging-driven care pathways, which I think is going to become a more and more important role for us to be playing over time, and then obviously for research, both on our ability to automatically extract these features, but also outcomes research, being able to tune how we're making recommendations for the downstream care of populations as we do so. So hopefully that's a bit of a whirlwind tour of kind of a future of radiology reporting and the role of a new ACR standard in that. But I hope that's been helpful to you as you think about this kind of new and exciting future for radiologists in our field.
Thank you, Dr. Alkasab. Our third speaker is Dr. Michalski, who will be speaking on the early applications of machine learning in imaging.
Thanks very much. Thanks to the organizers for making me part of this great conversation. So there's a lot going on in machine learning. It's happening all around us, right? So I think that we're seeing this narrative in the popular press that artificial intelligence is going to change a lot of our lives in ways that we don't quite yet understand or know the scope of. Microsoft in September created an artificial intelligence group, which is something that Microsoft has ought to do, except that this was 5,000 FTEs, a huge commit even for Microsoft. The tech giants are kind of coming together. This was the big five, and then Apple came in a little bit later to talk about the ethics of artificial intelligence, and importantly, now artificial intelligence can make pop songs. That's really important, and important for all of you to know. It sounds more like the Beatles than it does Justin Bieber or anything like that, so don't worry. And commensurate with that technology, that innovation, and the interest in that innovation, we've seen a tremendous amount of investment year over year. And again, the narrative really is about how artificial intelligence is broadly impacting our world. So for those of you who have an Alexa at home or have use Google Now or Siri, you'll notice that natural language processing and speech recognition is getting pretty darn good. There are systems that are now driving cars, which is interesting. That's sort of passé now. But NVIDIA created this great car, which actually learns how to drive based on inputs from the driver, the human driver, which wasn't the way that it used to happen. And part of the reason for doing that is because now these types of systems are resilient to inclement weather and dark light. It's pretty good at games. Some of you may have heard about AlphaGo, which was something that Google DeepMind created. Basically won 4 out of 5 games against one of the strongest human competitors. And for many in the room, I presume scheduling meetings is something that you think a lot about. There's actually artificial intelligence for that as well. So it's making a big impact in healthcare too, and that's why we're here to talk about it. And it's not just happening in the research community. So we may Some of you may have heard about the work that came out of Sebastian Thrun's lab at Stanford on diagnosing melanoma, and some of the work that was happening out of Google Brain for retinopathy. But it's also translating to practice pretty effectively. There's over 100 startups in, not just in healthcare AI, but healthcare AI and sort of diagnostics. So there's a lot of activity here. Before we move forward, I just want to level set. A lot of people ask me the difference between data science and machine learning and deep learning. So just to level set, the data science, the term data science refers to this collection of capabilities that really belong to to computer science and statistics. Within data science, it's really this interdisciplinary field that pulls together various systems, various kinds of data, and tries to pull meaning from that data. Machine learning is a toolbox within the data science discipline, and within machine learning is deep learning, which is part of the reason we're talking so much about all this stuff today. So deep learning is a specific set of tools within machine learning, and machine learning is this toolbox within data science. But deep learning has turned out to be very, very effective at many, many tasks, some of which Jayashree talked about. Very briefly, to level set again, this is the way that they work at a high level. You start with some training data. You might have a couple thousand examples of dogs versus cats. You'll run them through an untrained neural network. So this is sort of a fresh neural network. And after you do the training, you sort of feed these in. And the weights between these connections of neurons will adjust until you get an ideal accuracy. You can then take that model with the embedded weightings and adjustments between the neurons, and you can now give it de novo data so that it can perform the classification tasks on its own. So that's really the power behind this technology. There are lots of applications here, and while we're going to focus on diagnostics today, there are applications within diagnostics, management, therapeutics, and population health. And it has implications for data management in imaging, laboratory, EHR, genetics, and all sorts of other feeds. For example, your Facebook feed, your wearable. These can be all important for your diagnostics. So I want to take one example, as lung cancer as a test case, to talk about all the different facets in which we sort of evaluate and implement this technology. So just digging in, this is not new news for anyone around here, but lung cancer is the leading cause of death worldwide, and we know about the USPSTF recommendations, and that it would add an awful lot of studies to our work lists. And we also recognize that there's an opportunity to improve here. So in studies that have evaluated interoperator variability, we see a pretty significant amount of interoperator variability within classification, specifically features and sizes of nodules. And this turns out to have implications for management. So we see that there's an opportunity to improve in the way that we evaluate nodules. But we also recognize that there is an opportunity to improve the way that we report this data in our product, which is the report. And Terry talked a lot about this. Today, we identify the nodule, and through prose, we dictate the features and the size. But imagine a world in which you're extracting the data, and through machine learning, you're actually discovering features and codifying them into a structured data format. And then from there, you can take that structured data and implement guidelines. Again, some of this is what Terry touched upon, but imagine the power that comes from actually having repeatable longitudinal data that's extracted with machine learning. You're moving from simply a prose report to actual advice and data that can be tracked over time. It's truly longitudinal. So how do you actually implement this? Well, at our institution, we've been thinking a lot about this. Now we're at a place where there's a lot of models out there, and the real struggle is how do you put them into our workflow? How do we evaluate them? So we've started that process. The way that we typically use these models is we put them into containers. We call them Docker containers, and we'll embed within those containers a lot of different functions. And you can see right there in box number 4 there, we have a lung nodule machine learning algorithm, but it's sort of embedded within this workflow that allows you to do all the pre and some post-processing steps. And the thing is, you can actually drop all sorts of things into that workflow. So you can drop in a cancer detection algorithm or any number of the algorithms that you've created or others have created. And then once you have the results out, you can capture those results and capture that feedback for online learning. So you can actually improve the model as it moves forward. So this is an important consideration, and I think the place that we're going now, we've found that these models are useful and pretty impactful. We've seen their validity in sort of the research environment, and now it's time to embed them within our workflow so that we can see how they actually work. So I'll give you some insight into the way that we currently do this now. Our first pass was just to get it into our packs. This is at Mass General. We start with clinician selecting a case from the work list. The case is displayed. The clinician selects a tab which opens up an HTML browser effectively. And the results of the machine learning algorithm are put in that HTML feed. So in this way, we can start putting the results of these machine learning algorithms into the actual workflow. This isn't the most elegant solution, but it's the first step. And we can actually start to capture some of the feedback through the same HTML pane. Another way that these models are being developed, I should probably touch upon the Data Science Bowl because it's relatively recent news. The Data Science Bowl is a competition, and data science, just in general, has been really propelled by competitions. In fact, the discovery that the utilization of GPUs in combination with neural nets could effectively, perform very effectively in a generic way in computer vision was actually through a competition like this in 2012. And since then, we've had several competitions, and the Data Science Bowl is one of the bigger competitions. It's $1 million in prize money and a lot of data, and this year it was on identifying lung nodules and detecting the ones that were likely to turn into cancer. And to give you a sense of how it's performed, this is again relatively recent. Was announced at a meeting, at GTC, in NVIDIA's meeting earlier this week. So in combination with lung-RADS, humans performed an AUC an ROC AUC of about 0.82. The models themselves performed about 0.87, and an interesting feature is that if you combined many of the top models, they performed the best, which was 0.89. Again, this task was to determine whether a nodule turned into cancer. Another way of attacking this problem is looking at the ecosystem around us in early stage. So the reason I'm talking about pulmonary nodules is because it actually is a fairly matured field. We've been working at this for a long time in computer-aided diagnostics. And now, in fact, there are more than 5 early-stage companies that are working in pulmonary nodule diagnostics based on deep learning. And so some of the work that we're doing at Mass General and Brigham is identifying which of these systems are effective within our own clinical practice. So the actual process of validating some of these tools is ongoing at our institution. So it's now I think the message to take away is while we're still creating lots of detectors, we're now in a world where we're starting to incorporate these into our practice and validate them. And I think that's the next thing to the next phase of this field for us. So switching gears a little bit, I'll talk a little bit about some of the applications. We have applications within a broad range within medical imaging, from breast lesions, pulmonary nodules I told you about, mammographic lesions, tomosynthesis. We have deep learning models for segmenting the left ventricle of the cardiac MRI, brain tumors, and the list goes on and on. There isn't a day that goes by that my Google alerts doesn't fire something off that we've found a new computer model, a deep learning based model that takes some medical imaging data and segments it or classifies it. So give you a little bit of a sense of what we do at the Center for Clinical Data Science at Mass General and Brigham, some of the models we're working on. We have a fairly robust pipeline. This is a little dated, but we've got about 23 different projects. Let's say this represents about 12 laboratories. And this is a range of different projects, everywhere from, again, medical imaging all the way to drug repurposing. Give you a couple of examples of some of the things we're doing. We're working with Ziad Obermeyer in the emergency room at the Brigham, and we all are familiar from our boards that chest X-rays do have features in them that could be indicative of a PE. These days, I don't know that we use them a whole lot because we have CTPE, CTAs for PEs, but we know those features are in those chest X-rays, and wouldn't it be nice if we could recapture those features to hone in on pretest probability? So that's one of the things we're doing, just trying to identify with some of those attentional maps, features within chest X-rays that we may be able to rediscover and mine for more accurate pretest probability. Lumbar spine segmentation. This is a time-consuming task, and we've started the process of identifying areas of stenosis that we can highlight and, again, put them into a structured reporting environment where they can be repeatable and tracked over time. Several projects coming out of Quan Zhang Li's lab. He actually won the competition for breast cancer pathology. We'll show you an example of that shortly for the Camelon 17 challenge, working in pneumothorax, in reconstruction, CT, and machine learning based annotation tools. So what you're starting to see is we're going beyond just classifiers to things that, for example, start to go into the reconstruction world and many of the tools that are necessary for making progress in this space, for example, annotation. To give you an example of how this might work in pathology, these are lymph nodes from a breast excision. And this is the data from the Camelon challenge. So you see the way the machine learning algorithm works is a sort of a patchwise evaluation of the image. And after screening through the image, the anatomical path image that's been digitally scanned in, you can identify places where it thinks there's cancer. And here's an example of manual identification by a pathologist. There's the deep neural network output, and you see that there's a high level of concordance with this task. So here's sort of an attentional map or a likelihood map, which you can read as the likelihood that the computer thinks that what it's looking at is cancer. I'll show you an example of some of the things that are coming out of the Martinez Center in deep learning. So as I mentioned, machine learning is being used for all sorts of applications beyond classification. We know that the way that MRI images are constructed are an inverse Fourier transform from K-space, and we also know that there are multiple methods for doing this depending on different situations. So the standard Fourier transform is an inverse Fourier transform, but there's other methods of sampling which require different kinds of modules effectively to do the the image reconstruction. It turns out that you can train neural networks on case space and examples of images to produce those images, right? So here's an example of a machine learning algorithm being trained on case space, some reference images from an inverse Fourier transform. You see that AutoMap, which is the technique being deployed here, gives you exactly the same image. Here it is, same thing with a coronal head. And here's an example of why this might be useful. This is a misaligned Cartesian Fourier sparsely sampled space. And what we find sometimes with hardware misalignment, you can get these kinds of artifacts, and it's interesting that the neural network sees right through that. So what we see is in each one of those 4 reconstruction methodologies, actually the neural network does a pretty good job of reconstructing. So in the end, this is all about the data, and this is just the beginning of the story. What the future looks like for us is, I think, beyond validating some of the tools that we have in our hands today, it's aggregating multimodality data, management data, therapeutic data, population health data, and essentially getting this all into the same location in a standardized way with the tools necessary to query that data. That's where we're going in model formation. And then beyond that, we need to start thinking about how we're going to validate these technologies. We actually have a lot of the models in hand now, and the question becomes, are they good enough, and how do we know? So thank you very much.
We'll invite the speakers actually up here. We're going to trade places with you and take questions from the audience. Any questions? Go ahead. Hey, Jamal. How's it going?
Good. For most of the focus for artificial intelligence and one Nodule and stuff is on diagnosis or recognition of the abnormality. Is your group also looking at the use of deep learning and artificial intelligence in processes, improvement of processes? For example, at Yale, we are looking at a project that will help us recognize, by embedding this in the scanner, helping us recognize which studies to read first. For example, if a head study pops up, is there a need or not? It may be wrong. That's not, so it doesn't have to have that detailed analysis. And similarly, there's a lot of talk about appropriateness of ordering and help with that, but what about appropriateness of protocol for that indication? The protocol is right or not. So is your center actually looking at the entire process of radiology workflow and just not the recognition of pathology or analysis?
Yeah, that's a great question. In the actual task of so what the center does is essentially creates resources for a number of investigators across the institution. So one of the things I didn't talk about is we have clusters, we have data scientists, and we have data engineers. And what we've found is today, what I think a lot of the interest is developing these models and very quickly dropping them into workflow. But if you and that's sort of a specific phenotype. But if you step back, there's a lot of phenotypes of machine learning problems that are even broader than the ones that I mentioned. Beyond diagnostics, operations is a big one. Appropriateness is a big one. For us, it's just sort of there's so much greenfield. The first step for almost everything is a couple things: aggregation of the right people, the right compute, and aggregation of data kind of in the same location. The next thing will be sort of operational metrics. Those are a little harder to capture sometimes, but certainly on the radar.
And one of the things I can just say is that I think maybe some of the focus of that is that without being too self-centered, I think the assist technology that's starting to come out and that vendors are starting to incorporate into their products is actually starting to create this first kind of input for machine learning to actually get into the clinical. I'm sure as you're exploring your project that you're finding that there's big challenges in sort of automating the process by which these things can come into it. But at least on the reporting process, we're now starting to have developed this channel by which things can make their way into the reporting process and figure that out. And we had been doing that kind of even before this new golden age started. And so that may be a reason for some of that apparent current emphasis on that area of tools. But we're certainly interested in, and I think actually that a lot of the great effects for radiologists will be in kind of these ancillary rather than sort of that central reporting task.
Perfect. Any questions? Dr. Brink.
I want to ask Jayashree, as you look at machine learning applied to MR imagery construction, what features will we see most likely improved? Processing speed, precision, spatial resolution, temporal resolution?
So at this point, I think all of the above. I think the fastest we're going to see is probably just quicker data acquired better data acquired more quickly, so improved resolution with lower scan times. That is something that I think we'll see soon. In the long term, people have been talking about MR fingerprinting and how to optimize that, so trying to get, again, multiple contrast done more quickly. So how do we get the fastest path to the most information from an MR fingerprinting perspective? There's talk about, do we even need the image reconstruction at some point, or can we just go from the case-based data to optimize what we want to do for the pathology that we're trying to find? Is the visual image something that a human needs, and is a best acquisition for a machine the same as a best acquisition for a human? And those are definitely far out issues, but I think those are things that people are thinking about. Is perhaps it's not obvious that the best acquisition for us to interpret an image is the same that a machine would need. So,
and I'd say that there's often talk about in the same vein, which is do we need the images, or I often talk about where do you need to insert areas of explicability. It's very clear for us to feel comfortable with these machines. We actually have to, the outputs of these neural networks, we have to see the images. But I think what we're finding is if you increase the amount of data, then you get closer to these end-to-end architectures, actually start to work a little bit better. With the challenge from the Data Science Bowl, everyone did post-processing, pre-processing steps, all of the winning competitors. So it wasn't pure neural networks. But most people felt that the reason for that was basically data availability. So in a way, there's a belief, whether it's justified or not, that if you increase the amount of data, then eventually you'll get to a point where you don't need those pre-processing steps. In fact, we saw that with Stanford's, with Sebastian Throne, because he used hundreds of thousands of images.
And I think one of the other potentials is that in sort of the just interpret from case-based, don't create an image at all is, kind of at the end of a spectrum that you might imagine where because there are clinical scenarios which are driving specific questions which require specific feature extractions, you may realize that in order to do a study in a particular way, that the resolution of the images, and therefore, depending on the modality, either the radiation dose or the scan time, can be reduced in a way that creates not no image, but an image that, you know, if you were going to try and use to do kind of what we currently think of as our reading process would be inadequate, but that is adequate to, but that where the data are adequate to do the kind of extraction to answer the specific clinical scenarios that are being spelled out, and where there are automated tools to help with the extraction of, you know, the specific relevant data features. And I think that might actually, in the nearer term, be kind of a more exciting way to do it. I think, you know, being able to deliver even lower CT doses or perform MR scans even more rapidly to answer specific questions might be would be an exciting development to come out of this.
In the back.
Just one more thing, going back, the other thing that people are doing is in terms of quality assessment. So can we, going back to the question of workflow and other things, can we detect that the images needs to be retaken, for instance? So again, things like looking at the case-based data or the reconstructed data can help with that. So is the image of adequate quality either for a human or for a machine, or do we need to go retake that? So.
All the way in the back.
Thank you for your talks. Presumably, for the near future, as this technology continues to improve, like the RADISys tools, where the system, I assume, can learn this sort of stuff in nanoseconds, milliseconds, and it takes human learners days, months to learn. How do you see resident training changing while radiologists are still making the final decision in the report? They still have final say at the end of the report.
Yeah, so actually, I think that to me, one of the implications of the developments that we've been talking about here in general is that radiologists have traditionally basically had two roles in the performance of these exams. The first one, and is the one that's kind of sub rosa, or has been sub rosa for us, has been the supervision of acquiring the images, right? I mean, if you've read a study, you are at least on record as being the person responsible for supervising how an exam has been done, even if it was done, you know, while you were home in bed at a hospital in, I don't know, another state even, right? And so that kind of, that supervisory role, first of, you know, the performance of the images has been kind of part of what we've had all along, in addition to, you know, providing our clinical expertise and impressions for the report. But I think a new component of that is going to be added to the role of the radiologist, which is the supervision of these various data extraction tools and the supervision of the creation of the relevant data, and making sure that, to the extent that that's been created by automated means, that it's something that that is sane, right? So I think having all of these tools be first training our residents to have all these tools be correctly applied, to know what the various things that are extracting are, and to know when they're likely to go off the rails, or when they're working outside of parameters, is going to be an important part of well, first of the learning that we all have to do, but then is going to be an important part of what we're going to be imparting to our younger colleagues as they develop.
There.
I'm wondering about the data set to train AI. I mean, I guess you talk about lots of data, lots of good data to actually get them trained well. And I see repeatedly lung nodule examples, sometimes see stroke examples. So far it seems like we are working in very few areas where we actually have the data. I'm just wondering if your thoughts and going forward with creating data set. This seems to be so among us. I don't think it can sit with even with a distribution as big as ours. How to get those data? What's the plan for that? Are there any ownership issues as well? I mean, for example, I've learned some of the data actually are owned by the tax system. So I'm just wondering if your thoughts and taking a back on all of this.
I'll give that one a shot. Hey, Alex, how's it going? So I think I think it depends on the problem. One of the things that we've seen pretty clearly is that well annotated data is probably more valuable now than sort of poorly labeled data. So small sets of well-annotated data is probably more valuable than larger sets of poorly annotated data. So we've seen that tasks on, say, the left ventricle segmentation, where there's a high contrast to noise, you could probably get away with annotating hundreds of images, and it will perform pretty well. So in some ways, in some tasks, this notion that you need a huge data set to perform the task is actually not true. On the other hand, when the signal to noise is just too low, then you do start to run into these problems, or the number of classifiers that you want, the number of classes that you want to deploy increases, then you do have to start considering what the scale of the organization is that you're in, your ability to get that data. So it ultimately all begins with the question: what is it that you're trying to solve? And that's often a balancing act with, Jayashree and I were just talking about that. This is often a balancing act between, you're creating a resource like a data commons without a specific question in mind, and very specific questions that require specific annotations, and probably you could determine how much data you need. So there's always going to be a balance between those things, and to the extent that you have a couple like long poll types of questions to define what your data lake looks like, that's helpful. I think the second question, which is about data ownership, is probably a longer conversation. I might give it to Ben to talk about that one. But I think that there's sort of the way that legally data is owned and sort of the perception of ownership as well that you have to consider in this. So in some instances, the organization does own the data, but you can look at, if you Google the NHS's London hospital with DeepMind, you'll see that there's, because that data is from patients, and there's a sense that the patients have a stake in that, that if that isn't respected, that you get into some trouble. So that's the best way that I know how to answer that. You have to consider both of those things.
I'm going to go all the way in the back.
Yeah, hi, is it safe to say that you guys all subscribe to an AI enhancement theory in terms of parameter futures versus replacement?
Yeah. So yes, I think that's.
Will this be the Association of University Radiologists or the Association of University Robots?
Exactly. So I think the answer is that certainly in the short term, it's going to be an enhancement process, and that provides a number of advantages for both the people who want to make these tools and sell them, and for the radiologists, for radiology as a practice, provided that we're able to embrace that, right?
So what if you're wrong? Would it be wise to develop alternative strategies for a post-interpretive world?
Obviously. But I don't think anyone's sort of imagined what that is, and also partly because that would require such a large singularity of technology development. It's such a different plane from where we are right now that it's very difficult to make plans around that. And I'm sure.
Yeah, I think so. I think the answer is yes, but it is hard to plan for all these reasons, as well as the externalities about your world start to break. The assumptions start to break down. So, for example, if we have indeed created a system that now essentially obviates a radiologist, then actually the world around you has changed to such a significant degree that you may not actually be thinking about radiology at all, because now truck drivers don't have jobs. All the clinicians are either out of work or soon to be, and I hope that we've solved some bigger socioeconomic considerations. So, what's today?
We'll leave the hand waving out there. Let's go.
I want to continue this line of inquiry because it really is what we need to be thinking about.
I think all of those are going to be interesting questions, and I think they're going to be answered mostly outside of groups like radiologists. I think that the technology that's going to enable these jumps that I think will be disruptive, not just for radiology, and probably, as Mark was suggesting, not first for radiology, but sort of more broadly in our society, and reshape our society, is going to happen sometime, or could happen sometime. But the shape of all previous technology revolutions is that they sort of peter along in the low part of an S-shaped curve for some indeterminate period of time, and then they explode. And it's been very difficult, even for people who've tried to stick machine learning tools on it, to make good predictions about when a technology is going to make a jump to an exponential phase of the curve. So I don't have any idea, and I don't think anybody who claims to is telling the truth about when AI may make a jump like that would be affecting our lives in such a significant way. But I do know that in the meantime, there's going to be kind of this lower level of helpful enhancement kinds of things, and that it behooves us to really be trying to embrace that, and partly as a way of being prepared for a broader jump in technology.
Just really briefly, I mean, whenever I think about this question, simultaneously I have the vision of the first time I saw a neural network work, and they really do work. I mean, it's pretty amazing. They really do work. On the other hand, I just can't get my Outlook inbox to sync appropriately, and so and how long have I been dealing with that? So we live in this dichotomous world where there's a lot of interesting science, but I think actually the data engineering components are some of these rate limiting steps. So while you might have exponential growth in the ability to perform classification tasks, it still is going to be hard to get all that data in the same place all connected.
Nice. Go ahead, back.
So one of the things is, it sounds like at MGH you guys are implementing a number of machine learning algorithms. With that increased reliance on the algorithms and utilization, the medical legal environment is going to change a little bit, where it's going to go from negligence or malpractice to product failure. So has your institution thought about that and thought about ways in which to tackle it?
I can speak to that because I have been thinking about that question for our institution. And that's exactly right. Well, you're going to have a shift from it's going to be much more difficult for juries to decide, do you blame the radiologist or do you blame the machine? And also, do you blame the enterprise who put the machine in place? And so I think that what we're going to see with regulation, how do you certify these machines? We're going to see it with product liability. We're going to see it with labor law. When is it okay to allow a person who's been there for 30 years to be replaced by a machine? When do you have to find another thing for them to do? So I think that the explosion in power here will lead to those questions. At this point, I don't know what we can do, only because the courts are historically even slower than medicine in catching up. So I think that it's going to take the courts a long time to catch up this. We have seen in autonomous vehicles that the myriad of different regulatory responses you get, both on a local, a state, a federal level, and how that is mixed and how it's going to take time for that to even resolve itself. So I agree with you that shift is going to happen. What it means for us, I don't know that we can even, it's too early to even plan. Go ahead.
So to get back to Google Brain and the 106 startups in healthcare and AI, how much of this work, and what proportion is done by industry versus by academia? How do you keep in control of the process as so much industry investment is going into the field?
So a lot of the reason why we're having this conversation is because there's been a tremendous amount of industry investment in the world, in this world. The packages that we use on a day-to-day basis to create neural nets come out of industry, out of Google, typically. So a lot of the work that's happening in neural nets or deep learning, just in general, is centered there. But I would also say that historically, and I think it's kind of happening again, it's kind of recapitulating. Historically, tech companies have had a hard time translating those findings directly by themselves into healthcare. The first most visible failures were Google Health and Health Vault, and I know that there's continuous efforts, and I think that today at IT companies to translate this technology. But I'd say that my experience, and I'd love to hear what the other panelists have to say. My experience is that they definitely they're just waiting for us to help guide them. And it's not so much, do we have a seat at the table? We have a seat at the table. It's just up to us to sit down. And we really need to do that, and we need to do it now before someone else decides to take our spot.
Yeah, I think Mark's take on that is exactly right. Not just, I think most of them know or have realized that there are important aspects of it that they don't understand, and so are really eager to figure out how to engage us to bring these tools to bear, and even to identify the right problems to develop the new tools. I think that's an important part of this, and one where we can be very helpful to them as we go forward, provided that we do it instead of talking about doing it, because they will get impatient, because they are already, as Mark has alluded to, started investing huge amounts of money, and they have FTEs doing stuff and wanting to do stuff, and so they're going to be they're making things happen regardless of whether we're guiding them or not, but they would like us to guide them, and we're willing to be guided, so we should definitely take advantage of that while it's still the case.
And we have 3 minutes left, so I'll let you do a quick answer, and we have one more question I'm going to get to. Is that okay?
I was just going to say that they have the resources for annotations too, and they're spending a lot of money on that, which academic people don't necessarily have sometimes. So.
And then one last question, because that's the end of the last.
Deep learning, how much calculation is really being done? I get computers are fast, but when you say there's so much data, it's mind-boggling to me that can be processed. Is it being simplified, or is it, how much?
So these networks actually tend to have millions and millions of parameters, and the training takes a long time, and it can take anywhere from days to weeks or more. The companies like Google have large amounts of GPU access that allows them to do that fast. Once you have the trained network, getting inference on a new sample is much, much faster. You just have to go once through the network, and that is really fast. And that can almost be made happen. It's real time. It can almost be made happen on a mobile device or other. So training takes a long time, but inference is usually very fast.
Great. Well, thank you so much for everybody for attending this. Any additional questions, I'd ask that you come up and ask them directly. Thank you, and everybody have a good evening.